Hi all, welcome to the Residential Demand Deep Dive section of FES 2020. I am Usman Bagudu. In this session, I'll be taking you through the different ways in which energy use in the residential sector could change, the potential drivers of those changes, and the implications for energy networks of the future. We'll cover both heat and non-heat demand in the residential sector. We will not be covering electric vehicles as they are covered in the transport section. For a bit of context, in 2019, energy demand in the residential sector accounted for about 58% of all GB end-use gas demand, that is gas demand excluding gas for power, and about 34% of all GB electricity demand. It is therefore a very significant part of the overall energy use. Secondly, 15% of all UK carbon emissions in 2018 came from the residential sector, and this means energy use in this sector will have to undergo significant changes for UK to hit net zero target by 2050. In the next slide, we'll look at the key assumptions that underlie residential demand analysis within a defined scenario framework. Here you see how the framework has been interpreted to create the scenarios. We do this by assigning ranges to assumptions in a way that is consistent with the two primary uncertainties that the framework tries to explore. These are the level of societal change and the speed of decarbonization. The assumption ranges allow us to differentiate one scenario from the others. Here we highlight four key assumptions that impact both heat and non-heat demand, and what levels have been set in each scenario and why. Starting with the consumer transformation scenario, in this scenario, levels of home thermal efficiency are set high because of increased home insulation due to high willingness of society to change. This translates to lower underlying demand. Heat pump uptake in this scenario is also set high, and this aligns very well with high levels of appliance efficiencies, as heat pumps are generally more efficient than boilers. Because this is a high societal change scenario, we also assume consumers' engagement with their energy will be high as a result of greater uptake of time of use tariffs and energy storage to help manage peaks. In contrast, the system transformation scenario, which you see here in the blue header, has two important differences to the consumer transformation scenario. The first difference is that it has lower levels of thermal efficiency, and secondly, it has lower levels of heat pump uptake. This tells us that it is achieving net zero in a much different way, at least with respect to heating. For non-heat demand such as lighting, washing machines, TVs, the consumer transformation and system transformation scenarios are actually very similar. Staying with similarities, the leading the way scenario is similar to the consumer transformation scenario in many respects. The really important difference between these two scenarios is that the leading the way scenario relies more on hybrids to manage peak heat, and is also a little bit more ambitious when it comes to the efficiency of non-heat appliances. The steady progression scenario is really in a category of its own and differs from other scenarios in all important respects. It's got lower thermal efficiencies, lower appliance efficiencies, lower heat pump uptake, and so on. To summarize once again what distinguishes the scenarios. In the consumer transformation scenario, most of it is electrified, and both building and appliance efficiencies are high. In the system transformation scenario, the decarbonization of heat is done using hydrogen, and the scenario has lower levels of efficiencies. In the leading the way scenario, the solutions to decarbonizing heat are a bit more diverse. The scenario also has high levels of both building and appliance efficiencies. In the steady progression scenario, there is lower levels of societal change, and this means continued use of familiar technologies, and also the scenario features lower levels of efficiencies. Now that we've seen the ways in which the scenarios differ from one another, in the next slide, we'll see how some of these assumptions translate into actual numbers to get a sense of how far the assumptions are being pushed in order to meet the net zero target. To model demands, the high, medium, and low ranges discussed in the previous slides are converted to numbers. Here you see 4 key modeling input parameters and how they compare to today. The average heat demand per home, we see this falling by as much as 36% from 12.5 down to 8 megawatt hour per year in the leading the way scenario. This is as a result of massive retrofit of existing stock, higher standards for new buildings, and true user behavioral changes. Going to electric heat pumps, we assume performance improves significantly from today through closing of non-performance gaps, greater user engagement with smart controls, and the positive feedback effect of high levels of building insulation. The last point about building insulation is crucial in the consumer transformation and the leading the way scenarios, as it explains a lot about levels of demand in those scenarios, which we will see shortly. The last two assumptions on this slide are proportion of heat demand being met by heat pumps in hybrid systems and level of heat storage penetration. The parameters are assumed to be higher in consumer transformation and leading the way scenarios because of the high levels of heat electrification in these scenarios compared to, say, system transformation scenario, which decarbonizes heat through the use of blue hydrogen. Before diving into the future energy demand projections, I'll do a quick run through a few assumptions that do not change regardless of the scenario. Here you see the assumptions that are kept the same across all scenarios. They are kept the same because they either don't play a role in the framework or they function as standards. Regardless, they are a key component of modeling and therefore important to keep in mind. These include dwelling numbers, standards for calculating peaks, heat pump performance, and so on. In the next slide, we will look at the residential demand projections and the technologies deployed from the modeling of these assumptions. Here we see annual residential fuel consumption mix in the 4 scenarios, with the bar to the left showing the mix of fuels today. Regardless of which scenario we look at, we see that energy consumption in homes will be very different in 2050. The changes are obviously much more dramatic in the net zero scenarios. Overall, the annual residential energy consumption in consumer transformation, system transformation, and the leading the way scenarios are much lower than today. This is due to higher levels of energy efficiency from improved building fabric insulation or switch to more efficient appliances such as heat pumps for heat or LEDs for lighting. The reductions are also driven by individual choices about energy use, such as the use of lower indoor temperature settings or taking care to switch off devices when not in use. Demand reduction in the system transformation scenario is more moderate because of societal choice to achieve net zero targets using more familiar technologies, in this case, the use of hydrogen boilers. In the steady progression scenario, gas remains the main source of heating, although we'll be using less gas overall than today due to more electrification in off-grid homes and some improvement in home insulation as well as boiler efficiency. And by 2050, a good percentage of all gas being used in homes in steady progression will be hydrogen or biomethane in blended form. And finally, there's an increase in the other category, the light green segment in the top of the bars. And this is due mainly to heating technologies which include things like biofuels, energy from waste, and waste heat. A significant portion of current off-grid heating will be served by these heating sources. So we've seen the different ways in which net zero target could plausibly be met in the residential sector. In the next slide, we'll see the mix of technologies that these fuels are powering, with a particular focus on heat. Now a look at the residential heating technology mix. Compared to today, both the number and types of heating units installed will change. The increase in the number of units is relatively small and is due mainly to population increase, assuming we count hybrid units as single installations. In the consumer transformation scenario, we see most homes converting heat pumps, the yellow segment in the chart, through a combination of government support and societal buy-in for action on climate change. In the system transformation scenario, the switch is to hydrogen. The leading the way scenario is a middling scenario in terms of heating technology mix, featuring a mix of ordinary heat pumps and hydrogen hybrid electric heat pumps, the segment in green. In the steady progression scenario, we see a significant uptake in heat pumps in off-grid dwellings, but gas boilers will remain as popular as they are today. The number of homes on district heating is projected to grow significantly. Up to 10 times more homes will be on district heat than today by 2050, in at least two of the scenarios. Achieving these levels of uptake, as for other technologies, will require significant policy support. In the next slide, we'll see how these changes in technology mix impact peak demand for electricity and gas, as well as the relationship between annual and peak demands. Annual demands are a good indicator of the level of carbon emissions, but can fall short when it comes to predicting network requirements. Our assumptions about technology mix and how they are operated makes a big difference to the peak demand. Let's look at what this means for gas demand. We expect peak gas demand in the net zero scenarios, in this case, peak hydrogen demand, as there are no gas consumption in net zero scenarios, to decrease because of the high levels of electric heating in these scenarios. The decline in the net zero scenario is, however, less than the annual demand would suggest, and this is because of the widespread use of hybrids in this scenario. Boilers in hybrid systems, as you might remember from the previous slides and assumptions, are assumed to behave like conventional boilers on the coldest day of the year, in the sense that they meet all heating demand for that day, when they meet only 1/4 of total heating demand for the year. There's a similar pattern in steady progression scenario, where although overall annual gas demand declines slightly, as we saw in the previous slides, the number of dwellings being powered by gas, whether with gas boilers, hybrids, district heat, actually went up slightly due to population increase, and therefore the demand on cold winter days goes up a little bit in 2050 when compared to today. This means as we decarbonize using technologies like hybrids, we can expect a change in the gas annual to peak ratio. Now moving to electricity peaks. Electricity peaks in the residential sector will increasingly be driven by heat demand. In the consumer transformation scenario, over 70% of residential demand at peak goes into heating by 2050. The figures shown already account for peak shaving technologies like battery and thermal storage, as well as hybrid boilers and time of use tariffs. Now for a rough comparison of residential gas and electricity demand peaks. You might recall in the previous slides on assumptions, I showed that gas and electricity peaks are calculated using completely different standards. The chart on the left gives a comparison of the total electric and gas consumption throughout their defined peak days in gigawatt hours. The electricity number is a very simple estimate. We see that despite the increased electrification of heat, gas still delivered much more energy to homes in all but one scenario by 2050. Next, we take a step back and think about what this all means, what the analysis is telling us. So what conclusions or insight could we draw from the analysis? There are actually a few. I will go through some of them briefly. We need to improve the energy efficiency of our homes to achieve the net zero target through better building insulation and by more energy efficient appliances, both heat and non-heat. Natural gas boilers are not part of a net zero world. Almost all gas boilers today will need to switch to something else by 2050. Achieving these massive transitions will require considerable government support. In both the consumer transformation and leading the way scenarios, no new gas boilers are installed by 2035. But as well as government support, these changes will require coordinated behavioral changes at an individual level. We've also seen that energy demand in the net zero scenarios are considerably lower than today. In the consumer transformation scenario, for example, the energy required for heating will be lower by as much as 60% by 2050. And finally, we'll look at some of the lingering uncertainties and questions that are of particular importance to forecasting energy demand in the residential sector. The list here is only a selection from a long list and are really the continuation of conversations going on in different forums. The first is more of an operational challenge around how to better exploit the advantages of improved building insulation, thermal storage, and smart controls to manage peak electrified heat. Next is a question about what are the most effective ways of deploying low carbon technologies? And then, what is the potential scale of domestic DSR as demand-side response? And then, energy consumption for non-heat home appliances is seen to be falling faster than efficiency will suggest. Is this due to changing habits? Can we find out? And finally, could legislation help address the lag in energy efficiency improvement for wet home appliances like washing machines, tumble dryers, dishwashers, and so on? Please do get in touch with any ideas or options for addressing any of these questions. Thank you for listening. I hope you found that interesting. I'm now going to hand you over to Lara Modi for questions.